So when we talked about Bernoulli flow or using a Bernoulli equation, we use the conservation of energy, right? What do we know about the conservation of energy? It holds as long as there aren't non-conservative forces, as long as there isn't friction. Well, we have friction in water, and it's called viscosity. And so now we're going to talk about flows that we can't use the Bernoulli equation in because they have a loss of energy. They have viscosity that dissipates some of the energy of that flow. Before we get to viscosity, though, we need to talk about two different regimes of flow or types of flow. One of them is called laminar flow, and we can see laminar flow here. Here we have smoke rising, right? So here, everything looks nice and smooth, right? And if we were to draw the streamlines, how the particles were moving along there, we might see really nice straight lines. These are called laminae or layers. That's where laminar comes from. And they don't mix amongst each other, right? If a particle is here, there's no chance that that particle is going to end up there. It's always going to follow that nice, neat line straight up into the air with this smoke. Sometimes we call this streamline flow because it looks so nice and tidy. The streamlines fit together so well. But as the flow gets up here, it gets more complicated, right? And you get these cool vortexes and just sort of madness. It's just going all over the place. You don't know if a particle starts here, whether it's going to flow there or over there. It's going to move all over the place. And there's a sort of chaoticness to that flow. We don't know where something's going to go. And you can see that here. If I speed this flow up fast enough, it's not going to go over this, say this is a cylinder, nice and easy in a straight line. It's going to make a vortex behind there and start swimming around. And we see that, on a bridge, right? As the water from a river goes around a bridge piling, you see these vortices behind the piling, and that's called turbulent flow. So we need to have different rules for explaining laminar and turbulent flow because they're so qualitatively different from each other. Laminar flow, we can actually analyze analytically. What does that mean? It means that we can use math to figure out what's going to happen. Take pipe flow, for instance. Pipe flow is usually caused by a pressure difference, right? You have a pressure that's created, say, by a water tower, and that pushes water through your pipe to the end of your hose where the pressure is zero or the gauge pressure is zero. That's a pretty common circumstance where we build up pressure either by height as in a water tower, or maybe we have a pump that's using electricity or gas power to create that pressure difference. We can estimate the flow Q according to its resistance. So we know the pressure difference. This is the pressure at the bottom of my water tower. This is the pressure at the end of my hose. So that's what's driving the flow. And then there's certain things that are resisting the flow. And the result that you get is Q. So this is a very general equation for flow. And in fact, we can make a similar equation for the flow of current. And we'll do that in 152. But here, it's just pressure, driving force, divided by what's resisting the force equals how much flow you get. So what is R? R can be a bunch of things. If your pipe is really long, that's a lot of resistance. If you have a really narrow pipe, that creates a lot of resistance. If you have obstructions in your pipe, that's going to cause resistance. Finally, turbulent flow is going to create a more resistance because that water is going to be rubbing against itself. And then friction against the side of the pipe is also going to create resistance. So in order to think about R, we need to understand this friction. What is friction in the fluid? And that's where we're going to turn to viscosity. Friction in fluids is called viscosity. And we can think of it roughly as the thickness of the fluid, although there are limits to that comparison. But if you think about this image over here, this is honey probably, it's building up, right? It's above the surface of the water. Water wants to flow and be flat, or fluid wants to flow and be flat. but there's a resistance to that flow here, and that resistance is called viscosity. What's holding this honey here up above the surface of the water? It's the viscosity of the honey. And eventually it'll overcome that viscosity and flatten out, but it takes more time. Our flow rate is slower because this is such a viscous fluid. So really, more accurately, we can think of viscosity as resistance to flow within the fluid. This honey stacks up because there's resistance to that force of gravity, to that tendency to flatten. Viscosity affects pipes flow a lot because there's so much contact between the outside of the force, outside of the pipe, rather the inside of the pipe and the fluid itself. The pressure that drives pipe flow does work on the fluid. Viscosity and frictional forces do work against the fluid. So pressure is adding kinetic energy while viscosity is taking away that kinetic energy. Bernoulli's equation doesn't deal with those frictional losses, okay? So if we have significant viscosity, we can't use Bernoulli's equation. So when do we use Bernoulli's equation? When flows are really short, when there's not time. So if we talk about water spurting out of a hose, we can talk about the difference between the end of the hose and half a meter from the hose, because there's just not that much time for frictional resistance there. But in longer flows, we have to think about viscosity. So we return to our pipe flow. Here's our generic flow equation, and we want to think about what R is. And we came up with a list of things that could create resistance in a pipe. Now, we're not going to go through this math, but if we assume that the pipe is smooth and unobstructed, so we get rid of this guy, that the flow stays laminar, so we don't need to deal with turbulence, we can come up with a law of resistance that defines R. And this eta here is viscosity. This script L is the length of the pipe. R is the radius of the pipe. Okay, so we're taking into account this term, and that term. And this comes from a mathematical analysis. This isn't experimental work. As L gets longer, there's more resistance. As your fluid gets more viscous, there's more resistance. And as R gets bigger, your pipe radius gets bigger, there's less resistance. And that's a huge factor, right? Because that's a R to the fourth. So if I double the radius of my pipe, I'm going to reduce the resistance by a factor of 16. Now we're going to take this guy, put it up here, and we get Poiseuille's law. Ain't it a beauty? So this describes mathematically what kind of flow you're going to get when you have laminar flow in a round pipe. And this is only for laminar. So what do we do for turbulent flow? Turbulent flow math doesn't work anymore. It's too chaotic. We don't have a good theory for turbulent flow that is analytical, and so we have to do experimental flows. And what we've discovered is that there's a point where laminar flow turns into turbulent flow. And we can define this across a whole bunch of different fluids by noting that high velocity causes turbulence and low viscosity causes turbulence. If we have a high viscosity, it's easier to stay in laminar flow because the fluid doesn't want to go in crazy directions. It wants to go in the easiest way possible. So the onset of turbulence can be defined by what's called a Reynolds number. This is a non-dimensional number. If you divided out the units here, you'd find out that the units are nothing, which means it can be used with any system of units. It's a really useful idea that gets used a lot in fluid flows. But R is your density, V is the velocity of the flow, R is the radius of your pipe, and eta here is your viscosity. if this number, no matter what units you're, what metric system, British system, whatever, Martian system, you're going to have, if you get an NR, a Reynolds number above 3,000, you're going to get a turbulent flow. And so this is a really useful way to figure out, if I have these conditions in my pipe, am I going to be able to have a laminar or a turbulent flow? And if it's between 2 and 3,000, you'll get what's called transitional flow. But if it's above, if the flow is turbulent and you want to figure out flows, then you've got to use a whole set of experimental results that we won't get into in this class. But it's important to know that you'd have these two regimes or these two types of flow.